All right, so I guess we can get started. Maybe other people can trickle in as the time goes on. So since it's just the three of us, if you're comfortable, you can turn on the camera just so we can, get to know you better, and it becomes more informal, because the whole idea of this short call is that we kind of want to informally have a discussion among the Blitz users and share the solution, kind of teach you more about the libraries that are being used, and teach you more about the possible applications of this particular puzzle. And then I'll touch upon the new puzzle that has just gone live. So share a little bit of information about that. And it's a very relaxed, chill conversation. So you can feel free to ask questions anytime. You can feel free to ask us to stop and explain something again. Yeah. So welcome to the town hall. This is for the lip reading puzzle, as I just mentioned a few minutes ago. And in this, you'll be learning how to use convolutional neural network. And first, I'll just quickly recap the puzzle. And then Nimish, who's joining from AIcrowd, he's an ML engineer over here. He will be explaining the baseline, and he'll also be walking through the data set. Then we'll have an informal Q&A session, followed by a short discussion, and then finally introduction about the new puzzle, that the new fruit detection puzzle. So lip reading puzzle is all about identifying words from a silent video. As you already know, that in this puzzle, you have to identify words being spoken from a different video, from a silent video clip. And basically your task is to create a lip reading model that predicts a word spoken by a human face. And there are total 400 words, different words. That's the vocabulary. So you have to predict the word being spoken by a person in the video from this specific vocabulary. So something of this sort. Over here, we have words like move, mixer, tab, and goddess, and yeah. So these are different words being spoken in video outputs, and you have to identify them. So what does this puzzle exactly cover? What are you learning through this? What are the domains being covered? So one is building a 3D convolutional neural network. Second is a face detection technique using the mediapipe library. Third is you learn how to create custom data generators. And finally, you will be able to create a lip reading model for a video with a reasonably high accuracy. Some potential applications are, I'll prefix this by saying that we really believe in using AI for good. So that's kind of the central idea over here. And you can learn more about the ethics and the values we follow over here at aicrowd.com/AI_ethics. And yeah, so for instance, if you have a section of a video, of a larger video, then a small section is corrupted. So rather than having to reshoot the entire video, with a tool like this, that small audioless gap can be fixed. Second is, a lot of times CCTVs, cameras can be helpful for solving an urgent problem. But often either these cameras don't have any audio, or there could be a lot of background noise in the audio. So in both these scenarios, when there is no audio at all, or there's too much background noise, the words that are being spoken, that can be identified using this technique. So what we are doing for Blitz Puzzle is a very simplified, very small scale tool that we are doing, but the larger applications, a more real world application, can be linked to the corrupted audio, fixing audioless gaps, or having audio when there is no voice or there's too much background noise. So now I'll be handing over the baton to Nimish, who will be explaining the baseline and giving a walkthrough for the data set.
Yeah, thanks, Sneha. So let me just share my screen. Yes, just making sure if it's legible and everyone can read what's going on.
Yeah, it's okay.
All right, and just before we proceed, just because there's just one person here, how do I pronounce your name, just so I don't mispronounce it in the future?
It's Sasha.
Sasha, great, thank you. So before we begin, I was initially going to walk everyone through the entire puzzle, assuming more people are there, but just because you're here, we could take it a little bit, specific to what your experience with the puzzle is. So what have you had a chance to go through in the puzzle, like both the baselines?
So I didn't have much time to invest in solving the puzzle. So what I did was like creating the problem,
Got it.
looking at the first ideas to solve the problems, and look at on the internet at the different ideas I had. So basically what I did was more like a theoretical research of what possibility they were to solve the problem, but I didn't implement them completely
Okay.
because it took me too much time to search how in the documentation of the different library, how it works and things like this.
Okay, that completely makes sense. And to give me more context, so you work with ML on a regular basis, so or do you have like a good amount of experience? So
I had a few lectures on ML, but I more like studied on my own side. Like now I'm studying astrophysics, so I'm not doing lots of machine learning in practice in my
I see.
regular work. But what I know are the regular basics technique of computer vision, reinforcement learning, things like this. So I
Got
have
it.
the great basics and of how it works.
Great. Okay, cool. So, okay, that's pretty helpful. So in that case, what I can do is take it, like focus more on the concepts that are involved. So you get to take away these concepts and probably get an idea of how to implement it in your own field, which is probably the biggest takeaway for today. So to give you a brief walkthrough before we begin, what the pipeline looks like is how we're looking to solve the problem is we have the data set, which looks like videos and words spoken for each videos, as she said. So the pipeline looks more or less like we split the video into individual frames. To be clear, this is for the beginner solution. So this is for the first solution, which involves just using a random forest classifier. So we then split the frames. We then perform landmark detection on the frames. So every frame has all these key points on the faces detected, and we use the mediapipe library for that, which happens to be pretty fast and pretty good. And so what that looks like is just a large list of X and Y coordinates for each frame, with all the XY coordinates corresponding to each of the key points on the frame. And that varies as the key points change. I hope you're able to see this. Yeah. So what we then do is flatten this entire thing into a single long list of features. And essentially, this will be the list of all the features for all the frames present in a single video. So this, in essence, like represents the entire video and the words spoken in the video, as in the features of the words spoken. Now, in parallel, what we'll be doing is mapping the label to an integer, because we need to pass the integers to the model as class labels. So we'll be using a label encoder for that, which is just a simple module. All it does is take in a list of words, convert them to a list of integers, and in the future, you give it any word, it's going to give you the corresponding integer back, and vice versa. So that when you're done training and when your model during inference time returns an integer for you, it will map that integer back to a word. So your application is done end to end. So this will be the vague pipeline that we're looking into today. And talking a little bit more about the first approach, I'll be walking you through the bits of the notebook a little by little, and place a lot of heavy focus on the actual section which does the logic and stuff like that. So skimming through the initial bits where we install the AIcrowd CLI, this is just a tool that helps us like download the data set, authenticate yourself, so you can make submissions and evaluate them directly from the notebook without having to upload and stuff like that. So it's just a library which allows you to authenticate yourself, download data sets, and make your submissions. That's all it is. And in this case, we'll be downloading the data for the lip reading challenge and zipping the same data. And coming to the library that I mentioned that we'll be using, which is called the mediapipe library. It's a library that's written by Google, and it's just a library containing a bunch of useful operations related to faces and stuff like that, like detection of just the faces from a larger image, detecting key points and stuff like that. So in our case, we'll be making use of those two specifically, that is extracting just a section of the face out of an entire larger image, and also performing the key point detection as we noted. And this library, if you're not aware of what this is basically protobuf is a format that's quite familiar to JSON, where it's just a way to serialize and save data. And obviously, we want to be able to work with dictionaries. And since this library was written by Google, any results they return is returned in the protobuf format. So we need to convert that back to a dictionary before we can make use of the properties present in it, which in this case will be the X and Y coordinates of the landmarks. I will be taking a closer look at that down the line. And just a few utilities just to understand what the data set looks like, which is essentially we have those videos and also a CSV file with the video name corresponding to a word that was spoken in the video. That's the entire data set. And taking a look at a single sample, which I'm pretty sure you've seen, is essentially the lips are modulated to make them sound like, look like they're saying a particular word. So it is synthetically generated data, but at the same time, despite the fact that it's synthetically generated, it provides a great, test bench to compare different methods and like actually, understand what's the differences and what changes in what hyperparams could impact the results and stuff like that. So it provides a great test bench for that. And here we have data exploration section where essentially we've done a very simple thing, which is essentially show the frequency of occurrence of the words. And it's encouraged that people do their own exploration and add a lot of code over here so that they can gain more insights and play around with the hyperparameters or implement newer techniques and based on whatever insights they gather. And that can help them raise their score quite a bit. Coming to the data pre-processing section, I'll be skipping this part, which is essentially making sure that all the files are downloaded correctly and none of them were corrupted. Likewise, just making sure that the data set also contains all the words. I mean, all the words in the vocabulary are, present in the data set, and none of the words in the data set are out of the vocabulary, just to make sure nothing's corrupted. Coming to the actual part where we do something related to the problem in hand is using the pre-processing's label encoder class, which allows you to essentially fit a list of words to it after initializing it. And when you fit a list of words, every word, each one of those 400 words gets mapped to an integer between 0 and 399 in this case. And anytime you pass in a list of words, in this case, all the words in the data set, the column, it's going to automatically kind of cleverly map them all out to their corresponding integers. So it makes it useful when you're working with a large amount of data, as opposed to manually iterating over each word and maintaining a reference to each integer using a dictionary or something like that. This just makes it easy. And creating a final data set which contains the encoded labels and the data paths so that we can pass these directly as X and Y for the random forest classifier function. Getting to the part where we need to actually start generating the face landmarks and stuff like that, which we'll be using as features. So what that looks like is we make use of the mediapipe's face mesh module, as I mentioned. So it does support detecting multiple faces in a single image, but in this case, to keep things simple, there will be just single faces in each image. So what it looks like is you pass it an RGB image containing a face or something like it contains a face, and it processes it and returns this results object, which I did mention is in the protobuf format, but in this case, we'll just be taking a look at what it contains. So what it contains within itself is basically landmarks for multiple faces. And since there's just a single one in this case, this runs just a single time. And each face landmark, we will be unpacking this, but drawing it essentially just looks like this. So you get all the key points on the faces. There are 498 in total. So writing a utility function which takes in a video and returns a long flattened list of features. What it does is essentially uses the same module, and for every frame we do the face point detection, and we convert the results object into the dictionary using the protobuf to dict the utility function. And out of that, we unpack the X and the Y values for each key point, which are normalized. So we need to multiply them with the width and the height corresponding, respectively, and append it to a long list of features, convert that to an array and just flatten it. In the end, it's also important to make sure that all of them have the same number of features. different videos, they vary in number of frames they have. So you are not always going to get the same number of features in every video. But at the same time, it's very important to have the same number of features when you pass it down to a model or something like that. So what we'll be doing is just padding it to 25,000. 25,000 is not exactly arbitrary in this case. We just chose this as the maximum number of features approximately that they can access based on the video with the maximum number of frames, and multiplying that by the number of features in each frame. So any list of features that's less than 25,000 will just be padded with zeros. Essentially, give it a video, it will return a long list of features for that video. Now we need to process the whole data set to convert it to the format that the model can accept. And this is essentially what happens over here. We give it the entire data frame of all videos and it processes it, and we get a massive list of key points. So what that looks like is essentially 3,000 videos, and for every video there's 25,000 features, and the labels are also present as integers. Now, getting to the model that we're using, it did not plan on changing the default parameters of the random forest classifier, because people are highly encouraged to play around and see what affects the results and stuff like that. For example, I'll give you a little bit of context about random forest classifier before we do that. But essentially, in this specific scenario, we'll just be using the default parameters. And after instantiating the classifier, what you need to do is call the .fit method along with the X, which in this case is the training key points, which is 3,000 by 25,000 features, and also the labels, which is essentially a list of 3,000 integers corresponding to the word. And once you call .fit, it performs training phase based on the initialization parameters that you gave in creating this classifier. And then you can check how your model is doing by checking it on the validation data set by calling the .score on a trained classifier. And in this case, if I recall, the F1 score was around 0.76 with the default parameters. And to give you a brief idea of what parameters could really influence the results of a random forest classifier. For example, before that, I need to explain the fundamental concepts that it uses. So it uses something called bootstrapping the data set, and also selecting a subsection of the features, as opposed to having so essentially random forest is comprised of many decision trees, and typically every decision tree just takes a list of all features and tries various splits, and uses an information theory concept called information gain and entropy to calculate which split gives it the best odds of classifying accurately. So random forest builds on that idea, and what it does is essentially instead of taking the entire all the features present in the data set and also all the 3,000 items in the data set, it selects a subset of those features with repetition. So subset of those training data set points with repetition. So multiple samples could be present in a single, subset passed to tree one, let's say. And you'll also be selecting out of those 25,000 features, n number of features, like n different features. And this n number of features is pretty important because it has shown to affect the scores. I'll get to that in a second. So you pass it a subset of the features and it performs a classification and it gives a result. And likewise, every tree is trained on a different subset of those 25,000 features so as to eliminate any bias and therefore reduce also the amount of variance that is possible, because the traditional decision tree is very susceptible to, any slight change in the data it's pretty sensitive to that, and it could cause a massive divergence in the final results after training. So it prevents that variance, and it also reduces the amount of bias because features are randomly subselected. Coming to what useful values of n could look like, it has been shown that a square root of the total number of features could be selected as the number of features for each decision tree. And this has shown pretty good results. So yeah, you could look further into that later on with the default parameters. And that's how we can look at improving the score specific to your application and checking the score in the validation data set. And then finally, coming to making a submission in AIcrowd. So we will need to perform the same post-processing steps on the training data as we did for the testing data as we did for the training data. And we will be calling the .predict method on the testing key points because we don't have any classes or ground truths. So we call the train classifier .predict, and it returns the results. And if you could recall, these results are just a long list of integers corresponding to each word or each class. So we need to map that back to the words for which we'll be making use of the label encoder's inverse transform method. So give it a list of words, give it a list of integers, and the inverse transform is going to give you a list of words back. Using that, we'll just create a CSV file, and we'll be making a submission which should evaluate on AIcrowd. So so excuse me. So yeah, before we proceed, do you have any questions for me?
I have. So here the approach is not especially in deep learning, but my question was in mediapipe to extract facial features. What's hidden behind the simple functions that are already implemented by Google? Is that deep learning approaches to extract those features, or what kind of algorithm does it use?
Okay, so if I'm being honest, I haven't looked into the mediapipe library itself, but I'm assuming your question is, are they using an API to submit my results online, or is it like, are you asking me what exact model does it use locally?
Yeah, like what exact model does it look like? So I mean, for example, if the idea, the idea behind my question is, if I'm implementing a 3D convolutional layer, which is probably what you're going to introduce after, will I expect it to somehow extract features that are the same that mediapipe is doing, because it's also based on convolutional layer and deep learning, so it's going to extract facial features that corresponds to the ones that a CNN is going to extract?
Okay, if I'm understanding correctly, you want to know if the CNN is probably going to extract the same features as the mediapipe library has, like yes, we're doing manually using the mediapipe library. And to be honest, all of this happens in the Latin space, so it's really kind of impossible to visualize what's exactly happening. In this case, we are spoon feeding it like manually extracted features that we as human experts kind of deem would be useful for the task in hand, like the minimal amount of information that would be useful for performing this task. And when you use a CNN, all of this is happening in the latent space that most of the time you don't even know what features is it exactly looking for. In this very specific scenario, it's very likely that it will, it's kind of very obvious that it will zero in on the movements of the lips exactly and kind of tone out all the other features present in the face. For example, the features that we have consists of all the facial key points, but however, the CNN could learn to extract just the features around the lips and ignore and like just zone everything out essentially. It's kind of hard to deterministically say if it's exactly going to be using the same list of features, because again, it happens in the latent space in the CNN. But does that answer your question to an extent?
Yeah, it does. Thank you.
Okay, great. Yeah, and if everyone's okay, I'll be proceeding with the next approach that we have.
Just a second, I think Hemant just joined. So perhaps we can get an idea of his pre-existing level of knowledge, and then if he has any questions regarding the beginner's baseline or random forest. I know he joined a little late, but if you have any questions, Hemant, we can take this checkpoint to get them addressed.
Yeah, I agree with Nimish. We can't imagine what's going inside the network. So there are tools to visualize it, but right now it's a little hard to determine what's exactly going on. But like he said, it might not exactly zeroing in on the lips, but it probably might be developing features to differentiate between different lip movements. So yeah, and yeah, we can move on. Yeah.
Okay, so with that, I'll be going on to the next approach. I'll be mostly skipping through the initial setup part of the code because it's pretty much the exact same, except the additional step that we have in this case is instead of just instead of using the facial landmarks, what we'll be doing in this case is extract the let me skip to that specific section. Yes, out of the entire video, we're going to be extracting just the face. So again, mediapipe library has a thing called like ROI extractor, which allows you to extract the region of interest, in this case the face, and it can do this for multiple phases. But again, to keep things simple, there'll be a single phase in this time. You could also use a simple HAR cascade classifier or something like that. Just anything works. All you want is essentially the face, so we minimize the amount of information that we give to the CNN. So going through like what this concept looks like, right? So yeah, I have a few images to really drive home the idea of what it looks like. So traditionally, let's just ignore the fact that it's a 3D CNN for a moment. Like, let's just forget everything about 3D and just consider a normal CNN. And that's also important in this context. I'll be getting into why in quite a bit. So in a traditional image, we have 3 channels, R, G, and B. And when you feed in a single image to, let's say, any deep, our neural network written with PyTorch, TensorFlow, whatever, you are essentially feeding a large NumPy array or a tensor, you can call it either. And its dimensions are going to be the number of channels by the width and the height, or the width and the height, the number of channels, depending on what you're using to implement. So my point here is that it's a single image with all these 3 channels present in it, representing a single frame. Typically, when you want to encode information across time, which is important in this case because you want to know how the features are changing, so you can extract the word out of it, people typically tend to use things like RNNs and LSTMs. And obviously, they have their own issues related to optimization and like hyperparameter tuning, which kind of gets a little challenging in those tricky scenarios. So our main goal here was to introduce a topic, an approach that's not as common. It's quite overlooked, though, in my opinion, it's pretty effective in specific tasks. So essentially what it does is, let's say we have just a single grayscale image. We are going to have just 1 channel as opposed to 3. But you could instead take all the frames of a video, right? So let's say the video has 4 frames in this case. Take all the various frames and they're grayscaled already, and stack all of them into a single image kind of thing. So it's you could call this an image as that. It's what the model is taking in. It's a tensor of 3-dimensional tensor, which is exactly what a normal image is because they're color channels. Instead of having the color channels, we essentially have the frames of the video. And this is, again, mapped to a particular class. So this way, all the temporal information, like how the features change across time, are all encoded within a single dataset point and also its class. And we do not need anything like LSTMs, which provide a representation of the features from previous time steps. And you could scale this up to how many frames you want. In this particular case, you'll be looking at using 20 frames per video. This is heavily dependent on what application it is. And it's also very common that in reinforcement learning, like you mentioned, Sasha, that you skip some frames and take the next frame because you don't want too many frames, which gives very similar information. So you stack them all together and you provide it to the model, which returns an action. So that's where it's inspired from, and it is pretty effective, though it's very overlooked. And main goal was to introduce this concept. So how that looks in implementation, we'll be taking a look at it right now. So essentially what you'll be needing to do initially before you set up the whole thing is process the video files into their grayscale counterparts after extracting regions of, the regions of interest and saving a long list of images essentially. Soon we'll be stacking them all into a single dataset sample corresponding to a single class output. And in this case, we'll be manually implementing the label encoder, what the label encoder does, which is essentially, if I scroll back to that point, forgive the detour, essentially what it does is, yes, it's just essentially a large dictionary with all the words in the dictionary, and each one of them contains an index. It's this is just a manual implementation of that, but that's what happens behind the scenes. And you need to perform the post-processing for the entire data set. And after that, we can proceed to actually building the model. Before we build the model, we do need to create a custom data set generator, which is similar to a data loader in PyTorch if you implemented one. So essentially, because we don't want to create the whole data and load it into memory, because that can be pretty ridiculous. That can use a pretty ridiculous amount of memory when you're dealing with images specifically, and images with a lot of frames and high resolution. So what a sequence generator or the data loader in PyTorch allows you to do is dynamically load them into memory, like on demand. When you give it a particular index, it can load that into memory and it can give it to the model. And once it's processed, it's taken out of memory and the next batch is loaded in. So it's very efficient to use something like this, as opposed to loading the entire data set onto a variable and feeding that to your model. That's all the purpose of the data set generator is. So what we need to override are two methods called get item, which takes in an index parameter. I can get into specifics if you have questions. So I will just be explaining the basics right now. And you also need to override the underscore len, which returns the length of, the number of batches present in the data set. And these are all supposed to be implemented by you, but these will be called by PyTorch or TensorFlow, whichever you use, automatically when it's running through the training cycle. So yeah, and again, we will be making use of a very simple model. Before that, what a training batch of images looks like is essentially we have 224 by 224 dimensions of the image, the number of channels in the image, and the number of samples in the batch of items. And that's the X size, and the Y size will just mirror that in the sense that we have 4 batches, 4 samples, and each is a one hot encoded representation of its class. So instead of just being an integer 0 to 399, it's just a long list of 400 elements with zeros everywhere and just a 1 representing where the word is, so representing its class essentially. So it's a one hot encoded representation. Yes, I will get to how to kind of visualize it. I can answer it specifically to each question, but in this case, we'll be using a very simple model. It's highly encouraged that you play around and use different backbones like a ResNet 50 or any other pre-trained model like an ImageNet, whatever you would like to probably get better performance. But in this case, to drive the point home, the most important points here is what input looks like, which is a 20 channel input. And the dimensions of each channel is 224 by 224 by 1, representing the grayscale. So if it was not grayscale, it would be 3. So 1 in this case. And here's where the point of the different, the abstraction between 2D and 3D convolution neural network comes in. It's implemented as convolution 3D only because of the limitations of Keras. You could, in theory, just treat it as a 2D convolution with, as opposed to having 1 channel over here, you could, instead of having 20 channels over here, you could have 20 channels like so. And that makes it completely valid and a 2D convolution, because regardless of what the input dimensions are, as long as they maintain their, the form of every sample maintains its structure, the latent space will definitely figure out the same subset of features. Yes, so we will be constructing a very simple model, and before that, we'll be compiling it with the Adams optimizer with a very, a pretty average learning rate, 2e power minus 3. And the loss function we'll be making use of specifically in this case is categorical cross entropy, because we have one hot encoded representation of the classes, not the integers themselves. So if it were the integers directly 0 to 399, we'd be using the cross entropy loss function. And you could also pass in any list of metrics to it. Taking a look at the documentation tells you what strings can be passed to the list of metrics over here. And all of them will get logged during train time to tell you what's going on. Finally, to train it, you just essentially give it the train generator, which is essentially the data set, but passed through the dataset sequence generator. So you call it with the dataset, the column containing the X labels, which is the file names, and the column containing the Y. And it's important to know that you've overridden all of these in the functionality. So these are not specific to something Keras provides. These are all what you want, like you're defining all these. So it's entirely up to you what you want to provide and how you want the data set to be given to this. Point is, it returns a generator, which upon calling it with each index, like so, you pass it an index of a particular item. And so it could be anything from train, gen of 0 or 1, or if you want a subset, it's just like indexing a list, and it will return those samples. So it's essentially a simple generator. And Keras, like I said, makes use of those internally. It'll be called by them. That's why it's important to override the get item and the len function. So it knows how many batches are there and how to get each batch, like index each batch. Likewise, provide the validation data. So at the end of each epoch, it can validate itself and provide a score. And mention the batch size. These are just dummy parameters that people have to play with, and mention the number of epochs. And to give you a brief idea on the results and compare it with the random forest classifier, I believe this very simplified model and very simple approach with 30 epochs or so gave around an F1 score of like 0.65. In comparison to the random forest classifier, which came around 0.72, if I'm remember correctly. Obviously, it's highly encouraged that people play around with these values and kind of boost more. So there's a lot more potential in this method compared to the previous one, though the previous one can be simplified further. So yeah, we will be then just evaluating and understanding what the metrics are, taking a look at it. So we have a utility cell over here, which will directly give in your model and just validate, like the validation data set, it'll return the scores. So it can be useful to tweak your model a little bit, then come back to the cell and check how did those tweaks work, compare it with the previous tweaks and so on. Finally, making a submission is very similar to what we did earlier. We'll just need to pre-process the test set and pass it to the trained model. In this case, it's present inside, if I remember correctly, .model. So you need to call model.predict, which should be somewhere down below. Yes, model.predict with the test video frames, and convert those predictions, the encoded integers, back to the labels, create a data set out of it, data frame out of it, and yeah, submit it as a CSV file. And that brings us to the end of the explanation. And yeah, any questions?
I have. So you begin by explaining that the regular approach to the problem would be to use a STM because of the fact that it's MP4 the file is time series in frames, and it was actually the approach I would have implemented if I had more time to invest.
Mm-hmm.
And my question was, did you compare both approaches, so 3D convolutional layer and CNN boosted with LSTMs to take into account the time series features and to have just an idea of comparison between the two techniques?
No, we didn't compare the results itself. My goal with this notebook was to highlight a method that's seldom used or seldom explored. So it was essentially give people another tool in their arsenal, if you will, to try and experiment. So we did not compare on this particular scenario specifically, but from my personal experience, there have been scenarios where in LSTM, the optimization just did not lead to good results. And this approach worked well in my use cases. And there have equally been other scenarios where an LSTM outperformed the CNN kind of approach, even if coupled, after coupling it with a CNN. So the question works both ways. To answer both of your questions, so one, no, I did not compare both the approaches in this very problem. Two, the main goal here was to introduce this as a technique that's overlooked.
Thank you.
Right. So yeah, if you have any other questions or anything that's unclear, feel free to ask. All right, Sneha, over to you.
Yeah. So if there are no more questions, then we can move to introduction for the new puzzle that just launched a day or two ago, which is about fruit detection puzzle. So over here, you have to identify fruits on trees from static input images. So before I dive into the exact task, what's the rationale behind this puzzle? So something that has been happening in the farming industry for years is that they closely observe the vegetation and the yield to understand if the fruits and vegetables are growing as planned, if there are any insecticides or pesticides that need to be handled, to get an understanding of what the final yield is going to be. So this is something that was done manually, the observation and the tracking of it. But now, because cameras and smartphones are easily available, there are a lot more data that these farmers and agriculturalists are using to kind of understand how exactly these yields are happening and to measure them automatically. So that's kind of where we enter, that can we use these input images to identify the total number of fruits on a tree automatically using object detection tools? And that's the central problem. In this problem, you'll be learning a basic method, a knife method of using object detection using deep learning. There's also going to be intuition behind labeling single bounding boxes. You'll also be working with CocoJSON annotation formats. And finally, you'll be developing a state-of-the-art model to perform object detection out of the box. So more details of it is on the URL over here, or you can directly access it from your dashboard, the Blitz dashboard, and you'll be finding the new puzzle. There's also a basic starter kit along with it. And as some time goes by, we'll also be sharing the baselines the way we did for lip reading puzzle. Any questions about this? Any doubts? We'll be happy to address. Okay, so if there are no questions, there's a small request from my side. If you are comfortable, can you turn on your camera so we can take a really quick screenshot and like a group screenshot of the Zoom call to just memorize this event. Great, lovely. Let me just fix the view so I can. Lovely. Thank you so much. Thank you so much for coming. But one second, I'm sorry, just really quickly before we leave, I'm launching a small poll right now that should be popping up on your screen. And additionally, I would like your honest feedback on the Blitz product. So what was your experience with the Blitz puzzle in last 2 weeks? Did you find the puzzle explanation easy? Did you find the data easy to access? Were the beginner's baseline easy to go through? The advanced baseline, did you give it a shot? Anything. It could be the email communication. It could be the content on the puzzle page itself. It could be the baselines. So I would, and you can be as honest as you want. This is something that we want, like to what are the areas of improvement for us? That's what that's what I'm nudging for.
In fact, I find it really good, in my opinion. So it keeps the speed, baselines, etc. Just probably the thing that's complicated when you're not doing like AI regularly or developing is to like have to find like documentation or libraries, Python libraries that are really useful in some problems. And what could be interesting or helpful is to have links to those libraries with some explanation or just some text to explain what is doing this library and how it could be useful in such problem. For example, I didn't know mediapipe existed, so it could be a good like gateway to enter in the problem to have those link to those libraries that already exist and that implements methods that can be useful to have the first approach of the problem.
Okay, that was really helpful. That makes sense. Hemant, what are your what's your experience like?
Yeah, it's good.
All right, thank you so much for joining on a Sunday. I hope you guys have a good day ahead, and hope to see you for the next town hall, which will take place in 2 weeks' time. So yeah, all right, bye.